What if the moon was never meant to be humanity's second home? What if, despite all the glossy concept art and bold promises, the moon is actually one of the most hostile environments a human could ever try to live in? For decades, we've been told that going back to the moon is just a matter of technology, funding, or political will. But what if the real problem isn't engineering at all? What if it's biology and physics working against us? Tonight, we're not here to deny science. We're here to use it. Because when you strip away the optimism, the slogans, and the science fiction, a disturbing question emerges. Is it actually impossible for humans to live on the moon? Before we go any further, it's important to clarify something. Skepticism is not denial. Questioning feasibility is not rejecting exploration. And pointing out limits does not mean opposing science. It means respecting it. This channel doesn't exist to dismiss space agencies, astronauts, or decades of research. In fact, much of what we'll discuss tonight comes directly from mainstream physics, biology, and engineering studies, including concerns raised by scientists working within organizations like NASA and other international space programs. The problem is not that these issues are unknown. It's that they're often minimized, postponed, or framed as future engineering challenges rather than fundamental constraints. There's a critical difference between visiting an environment and living in it. Humans have briefly visited the moon. That part is not in question here. But living somewhere requires long-term biological stability, sustainable systems, and an environment that doesn't constantly degrade the human body. This video focuses on a simple but uncomfortable comparison: what the moon allows versus what the human body requires. We'll be relying on well-established principles: radiation physics, human physiology, environmental engineering limits, long-duration exposure data from spaceflight, no fringe theories, no secret documents, no hidden agendas, just the known properties of the moon and the known weaknesses of a human body. So as you watch, don't ask, could we build something eventually? Ask a more difficult question. Even if we could build it, could humans actually survive living there? That distinction changes everything. To understand why living on the moon may be fundamentally impossible, we have to start with something invisible, something silent, and something deadly: radiation. Here on Earth, you are protected every second of your life by two massive shields you rarely think about: the atmosphere and the magnetic field. Together, they deflect, absorb, and scatter most of the high-energy particles constantly blasting through space. The moon has neither. No global magnetic field, no meaningful atmosphere, no natural radiation protection, which means the lunar surface is exposed directly to solar radiation, cosmic rays, and high-energy particles from deep space. To put it simply, the moon is not just unprotected, it is naked. Earth's shield versus the moon's exposure. Earth's magnetic field stretches tens of thousands of kilometers into space, forming a protective bubble called a magnetosphere. When charged particles from the sun slam toward us, they're diverted around the planet, funneled toward the poles, or weakened before they ever reach the ground. That's why solar storms give us auroras, not radiation sickness. The moon, on the other hand, lost its magnetic field billions of years ago. Whatever weak remnants exist today are localized and useless for protection. There is nothing stopping radiation from striking the lunar surface directly. Every particle that misses Earth hits the moon. This isn't speculation. It's measured, monitored, documented, and it creates a problem no amount of optimism can ignore. But astronauts already went there. Yes, they did. And this is where the distinction between survival and habitation becomes critical. Apollo astronauts were on the moon for hours, sometimes days. They were not there for months. They were not there for years. And they certainly were not born there. Radiation damage is cumulative. It doesn't care how advanced your technology is. It adds up over time, hour by hour, cell by cell. Apollo missions were essentially sprints through a lethal environment, carefully timed to avoid major solar storms. Even then, astronauts received elevated radiation doses compared to Earth. Living on the moon would mean constant exposure, not brief encounters. That difference changes everything. Radiation over time, the numbers get ugly. Radiation exposure isn't just about intensity. It's about duration. On Earth, The average person receives about 2 to 3 millisieverts per year from natural background radiation. On the moon, measurements from lunar orbiters and surface instruments show radiation levels 10 to 20 times higher every single day. And during solar particle events, that number can spike dramatically in a matter of hours. A long-term lunar resident will receive in months what a person on Earth accumulates in decades. And unlike Earth, there is no atmosphere to absorb radiation, no magnetic field to deflect it, no warning system that can always protect you in time. One strong solar flare, arriving faster than predicted, could deliver a potentially lethal dose to anyone on the surface. You don't need a conspiracy for this. You just need physics. What radiation actually does to the human body. Radiation isn't like poison you can flush out. It damages you at the most fundamental level. It breaks DNA strands, causes mutations during cell division, destroys stem cells, alters neural tissue, increases cancer risk exponentially. High-energy cosmic rays are especially dangerous because they punch through tissue, leaving trails of molecular damage behind them. This isn't theoretical. Astronauts in low Earth orbit, still partially protected by Earth's magnetic field, already show increased risks of cancer, cataracts, cognitive impairment, cardiovascular damage. And that's in orbit, not on the moon. On the lunar surface, there is no fallback layer of protection. The damage doesn't just affect one organ. It affects every system simultaneously. The neurological problem no one likes to talk about. One of the least discussed consequences of long-term radiation exposure is its effect on the brain. Studies involving cosmic radiation simulations show potential links to memory degradation, reduced decision-making ability, increased risk of neurodegenerative conditions. This is especially alarming when you consider that a moon base would require constant vigilance, high cognitive performance, precision operations, emergency response under stress. Radiation doesn't just shorten life expectancy. It may compromise mental function while you're still alive. Living on the moon wouldn't just be dangerous. It could slowly erode the variabilities needed to survive there. Just build better shielding, right? This is where many optimistic arguments stop thinking critically. Yes, shielding can reduce radiation exposure, but shielding against high-energy cosmic rays is not simple. You don't block them with aluminum walls or thin habitats. You need thick layers of dense material, multiple meters of regolith or water, massive structural reinforcement, which raises several problems. Transporting that mass from Earth is unrealistic. Building it autonomously is unproven. Maintenance under radiation degradation is constant. One breach could be catastrophic. Even underground habitats, often proposed as a solution, would require significant depth and flawless structural integrity. And even then, radiation doesn't disappear. It seeps in, accumulates, finds weak points. Shielding reduces exposure. It does not eliminate it. Solar storms, the silent countdown. Perhaps the most terrifying aspect of lunar radiation exposure is unpredictability. Solar particle events can erupt suddenly. Some travel faster than warning systems can react. On Earth, we barely notice most of them. On the moon, a severe solar storm could mean acute radiation sickness, permanent organ damage, fatal exposure within hours. There is no atmosphere to buy you time. Living on the moon would mean living under a constant invisible threat, hoping the sun doesn't decide to remind you who's really in control. So now we circle back to the question that matters. Can humans survive indefinitely in an environment where radiation exposure is unavoidable, protection is artificial and imperfect, damage accumulates relentlessly, one solar event can be fatal? Visiting the moon is one thing. Living there, year after year, is another entirely, and radiation alone may already be a biological deal-breaker. But disturbingly, it's only the first problem, because even if radiation were somehow solved, the moon has many more ways to remind humans that it is not a place meant for life. Even if radiation could somehow be controlled, the moon presents another problem that is even more immediate and far less forgiving. The moon has no atmosphere. Not a thin one, not a weak one, essentially none at all. And without an atmosphere, human life doesn't just struggle, it fails instantly. What an atmosphere really does. On Earth, the atmosphere isn't just air you breathe. It's a multi-purpose life support system. It provides oxygen for respiration, pressure to keep bodily fluid stable, temperature moderation, protection from micrometeorites, a buffer against radiation and solar wind. Remove it, and the human body is no longer operating in a survivable environment. The moon offers none of these. No air, no second chances. The most obvious problem is the lack of breathable oxygen. On the moon, there is no oxygen-rich air, no nitrogen balance, no carbon dioxide cycling, no natural replenishment. Every single breath would have to be artificially supplied. That means perfect life support systems, operating 24 hours a day, indefinitely. No leaks, no failures, no degradation. Because outside your habitat, there is nothing. The pressure problem most people overlook. But oxygen alone isn't enough. The human body evolved under constant atmospheric pressure. Remove that pressure, and biology begins to unravel. In a vacuum, liquids boil at body temperature. Blood doesn't circulate properly. Gas expands in tissues. Cells begin to rupture. This process is called embolism, and it doesn't take long. Without pressure, a human loses consciousness in seconds. Irreversible damage follows shortly after. This is why spacesuits aren't just clothing. They are miniature pressurized worlds. Living on the moon would require living inside sealed pressure vessels at all times. One structural failure, one microfracture, one unnoticed seal breakdown, and the environment instantly becomes lethal. Micrometeorites, a constant invisible assault. On Earth, the atmosphere burns up countless micrometeorites every day. We never see them. We never feel them. On the moon, they hit the surface directly, constantly. Tiny particles traveling at tens of thousands of kilometers per hour strike the lunar surface with enough energy to puncture thin materials, degrade surfaces over time, create secondary debris. A long-term habitat will be under continuous bombardment. Not dramatic explosions, but slow, relentless damage. Every hit is a risk. Every impact is cumulative. Every repair requires exposure. There is no atmospheric shield to take the hits for you. Thermal chaos without an atmosphere. An atmosphere also stabilizes temperature. The moon has no such buffer. As a result, temperatures swing violently. Blistering heat in sunlight. Deep, crippling cold in shadow. And because there's no air to distribute heat, these changes happen rapidly and unevenly. A habitat in sunlight can overheat. A structure in shadow can freeze. Materials expand and contract repeatedly. Over time, this leads to metal fatigue, seal degradation, structural stress. Earth buildings rely on stable thermal environments. Lunar habitats would be in a constant battle against physics. Artificial systems must never fail. On Earth, when systems fail, the environment is still survivable. On the moon, failure equals death. Every aspect of survival would depend on artificial systems. Oxygen generation, carbon dioxide removal, pressure regulation, temperature control, structural integrity. There is no backup environment. There is no margin for error. There is no stepping outside to fix things safely. Even routine maintenance would involve significant risk. Living on the moon wouldn't be living in a place. It would be living inside a machine every second of every day. The psychological weight of total dependence. This isn't just a technical issue. It's a human one, knowing that one malfunction ends everything. One seal failure is fatal. One miscalculation is irreversible. Creates constant psychological pressure. Long-term habitation requires not just survival, but mental stability. Even with perfect air, perfect pressure, and perfect radiation shielding, the moon still presents a brutal enemy, temperature. Not just cold, not just heat, but violent, relentless extremes that push technology far beyond what was designed to endure long-term. A world without moderation. On Earth, Temperature is moderated by atmosphere, oceans, weather systems. Day-night cycles measured in hours. The moon has none of this. A single lunar day lasts about 29.5 Earth days. That means roughly 14 days of continuous sunlight, followed by 14 days of continuous darkness. No sunrise relief, no nightly cool down, no gradual transitions. Just extremes, locked in place for weeks at a time. The numbers are worse than they sound. In direct sunlight, the lunar surface can reach plus 127 degrees Celsius. In permanent shadow or during the long lunar night, temperatures plunge to minus 173 degrees Celsius. That's a swing of over 300 degrees Celsius. On Earth, very few materials experience anything remotely close to that, and certainly not on a continuous cycle. Every lunar structure will be forced to expand, contract, freeze, and overheat again and again and again. Physics doesn't negotiate. Material fatigue, death by repetition. Extreme temperature changes don't usually cause immediate failure. They cause something more dangerous, slow degradation. Repeated expansion and contraction leads to cracks in metal, seal failures, brittle components, warped structures. On Earth, these effects happen over decades. On the moon, they can happen much faster because the temperature differences are sharper and the transitions harsher. A habitat doesn't need to explode to become uninhabitable. It only needs a seal to weaken, a joint to fail, or a panel to fracture. And once again, failure isn't inconvenient. It's fatal. The 14-day lunar night problem. The long lunar night is especially dangerous. 4 2 full Earth weeks. No solar energy. Constant deep cold. Increasing power demand. Everything must run on stored energy. That means massive batteries, nuclear power sources, or systems that have never been tested under lunar conditions long-term. Energy storage is not a solved problem at this scale. Batteries degrade. Nuclear systems add complexity and risk. Redundancy adds mass, and mass is the enemy of spaceflight. Cold is harder than heat. While overheating is dangerous, extreme cold is often worse. In intense cold, lubricants freeze. Electronics behave unpredictably. Materials become brittle. Mechanical systems seize. A system that works perfectly during lunar day may fail during lunar night. Now multiply that risk across. Life support, power generation, communication systems, structural integrity. Every subsystem must function flawlessly through 2 weeks of darkness and cold, over and over again. Heat dissipation in a vacuum. Here's a problem that sounds counterintuitive. In space, getting rid of heat is actually harder. On Earth, heat dissipates through air. On the moon, there is no air. The only way to shed heat is through radiation, conduction through solid materials. This means equipment can overheat easily in sunlight. Cooling systems must be oversized and complex. Heat can become trapped inside habitats. Managing temperature on the moon isn't about warming up or cooling down. It's about doing both simultaneously without error in a vacuum. Technology versus time. Short missions can tolerate extremes. Long-term habitation cannot. Every extra day increases. Wear, stress, probability of failure. Technology doesn't fail because it's bad. It fails because time exposes every weakness. And the moon accelerates that process. The question that matters. So ask the real question. Can technology survive indefinitely in a place where temperature swings are extreme? Day and night last weeks. Cold can disable systems. Heat can't easily escape. Maintenance requires constant exposure. Or are we assuming that machines can simply endure what biology already struggles to survive? Because on the moon, time is not neutral. Time is an enemy, and it is always working against the systems keeping humans alive. And no human society in history has evolved under conditions where the environment itself is instantly lethal without technology. The core question, again, so ask yourself, can humans truly live in a place where there is no air, no pressure, no thermal stability, no natural protection, no forgiveness for error, Or are we confusing temporary survival with habitable reality? Because the moon doesn't just lack comforts. It lacks the very envelope that makes life possible. And without it, every breath, every movement, every second depends entirely on systems that must never fail. And the moon has many more ways to push those systems beyond their limits. If radiation is the moon's invisible threat, and temperature its brutal one, then lunar dust is something far more insidious, because it doesn't arrive all at once. It accumulates, it infiltrates, and over time, it destroys both machines and people from the inside out. Not dust as we know it. When we hear the word dust, we imagine something soft, harmless, easily brushed away. Lunar dust is nothing like that, because the moon has no atmosphere, no wind, no water, no erosion. Lunar dust particles have never been rounded or smoothed. They are microscopically sharp, jagged fragments created by billions of years of meteorite impacts. Think less sand and more glass shards. Electrostatic and unavoidable. Lunar dust also carries a strange and dangerous property, electrostatic charge. Under constant solar radiation, dust particles become electrically charged, causing them to stick to suits, cling to equipment, infiltrate seals, float and levitate near the surface. Apollo astronauts describe dust that refused to come off, no matter how much they brushed or wiped. Every time an astronaut enters a habitat, they bring the moon inside with them, and once it's inside, it stays. A respiratory nightmare. The real danger begins when that dust becomes airborne in a pressurized habitat. Lunar dust particles are small enough to penetrate deep into the lungs, bypass natural respiratory defenses, lodge permanently in tissue. Because of their sharp edges, they don't behave like normal particles. They can tear lung tissue, trigger inflammation, cause long-term respiratory damage. Apollo astronauts reported persistent coughing, sore throats, eye irritation, sinus congestion, and those were after brief exposure. Long-term habitation raises disturbing questions: chronic lung disease, toxic buildup, increased cancer risk, immune system stress. Unlike Earth dust, lunar dust cannot be safely expelled or broken down by the body. Equipment killer. Machines fare no better. Lunar dust is abrasive. It grinds away at seals, bearings, joints, visors, filters. During Apollo missions, dust caused suit joint stiffness, scratched helmet visors, degraded seals, equipment malfunctions. Now imagine this happening not for days, but for years. Every moving part becomes a failure point. Every seal becomes temporary. Every system degrades faster than expected. And replacing equipment on the moon is not like ordering parts on Earth. No natural cleaning mechanism. On Earth, dust is washed away by rain, wind, weather, gravity-assisted settling. The moon has none of these. Once dust settles, it stays, it accumulates, it spreads. Habitats would slowly become contaminated from the inside. Filters clog, surfaces degrade, air quality worsens. There is no natural reset. The psychological toll of contamination. Imagine knowing that your air contains microscopic blades. Your equipment is slowly grinding itself apart. Your body cannot fully expel what you inhale. This isn't a dramatic catastrophe. It's a slow erosion of safety. And those are often the hardest environments for humans to endure, because nothing ever feels fully clean or fully safe. Why this problem is underestimated. Dust doesn't sound dramatic. It doesn't explode. It doesn't freeze you instantly. It doesn't irradiate you in one moment. But over time, it undermines everything. Radiation kills silently. Temperature kills brutally. Dust kills slowly. And the moon has more dust than it has mercy. The question that lingers. So ask the uncomfortable question. Can humans truly live in an environment where the ground itself damages lungs? The air becomes contaminated. Equipment degrades constantly. There's no way to fully clean or escape it. Because on the moon, even the surface beneath your feet is working against you. and it doesn't need to hurry. Time is on its side. Up to this point, we focus on the moon as an external threat: radiation, vacuum, temperature, dust. But now we reach a problem that can't be engineered away: the human body itself. Because even if every machine worked perfectly, the moon still asks humans to live in a condition we did not evolve for, 1/6 of Earth's gravity. And biology does not adapt as easily as optimism suggests. Gravity is not optional. Every system in your body assumes one thing: constant gravity. Your bones, muscles, heart, blood vessels, inner ear, even your cells are shaped by it. Remove gravity or drastically reduce it, and the body doesn't stabilize. It deteriorates. We already know this from astronauts living on the International Space Station, where microgravity causes measurable damage in weeks. The moon isn't microgravity, but 1/6 gravity may not be enough to protect the body long term. Bone loss, a structural failure. Bone is living tissue. It constantly remodels itself based on stress. Reduce that stress, and the body starts removing bone. In space, astronauts lose 1 to 2% of bone density per month, even with intensive exercise. On the moon, gravity is still too weak to load bones normally. Lower limbs receive far less stress. Spine and hips are especially vulnerable. Over years, this could lead to fragile bones, increased fracture risk, permanent skeletal deformation. No medication has fully stopped this process. Exercise slows it. It does not reverse it. Muscle atrophy. Strength fades quickly. Muscles exist to fight gravity. When gravity weakens, muscles waste away. Astronauts experience loss of leg strength, reduced endurance, decreased coordination. Now imagine living in low gravity from birth. Muscle development may never reach Earth normal levels, which raises serious questions. Could lunar-born humans ever function on Earth? Could they survive Earth's gravity at all? A moon colony may create bodies incompatible with their home planet. The cardiovascular system breaks the rules. Your heart and blood vessels are gravity-dependent. On Earth, blood pools downward. The heart works against gravity. Vessels maintain pressure gradients. In low gravity, blood shifts toward the upper body. The heart weakens. Blood pressure regulation changes. This leads to dizziness, fainting, reduced exercise tolerance, long-term cardiovascular changes. These effects persist even after astronauts return to Earth. Now imagine they never leave. Balance, orientation, and the brain. The inner ear evolved for Earth gravity. Change gravity and the brain struggles. Effects include disorientation, motion sickness, impaired coordination. The nervous system can adapt partially, but there is no evidence it can adapt perfectly or permanently. A lunar environment may always feel subtly wrong. That constant mismatch adds stress to both body and mind. Reproduction, the unknown territory. Here's where speculation becomes unavoidable, because we simply don't know. No human has ever conceived in low gravity, carried a pregnancy in low gravity, given birth in low gravity, raised a child in low gravity. Animal studies suggest serious risks: abnormal development, impaired organ formation, skeletal deformities, gravity influences, cell division, embryonic orientation, nutrient transport. The moon may not just harm adults, it may prevent healthy reproduction entirely. Children and developmental risk. Children are not small adults. Their bodies are still forming. Bone growth, muscle strength, organ positioning all depend on gravity. Growing up in 1/6 gravity could result in permanently weakened skeletons, altered organ structure, inability to tolerate Earth gravity later. A moon-born human might be biologically trapped on the moon, and that raises ethical questions no one likes to confront. No evidence of long-term adaptation. This is the most important point. There is no evidence that humans can fully adapt to long-term low gravity. We have short-duration spaceflight data, limited long-term orbital data, zero multi-generational data. Every indication we do have points toward progressive degradation, not stabilization. Technology can support the environment, but it cannot rewrite human evolution overnight. the question that can't be ignored. So now ask the most uncomfortable question of all. Even if we solved radiation, atmosphere, temperature, dust, would the human body still fail slowly, silently, inevitably? Because the moon doesn't just challenge our technology, it challenges our biology. And biology does not negotiate. It responds only to physics. And physics does not care how badly we want the moon to be home. After examining radiation, vacuum, temperature, dust, and low gravity, a clear picture emerges. The moon is far from a hospitable home. But the story doesn't end with science alone. It deepens when we ask the questions nobody seems to answer. Why hasn't a permanent moon base been built? It's been over 50 years since humans first set foot on the moon, yet there is still no permanent presence. We have the technology, at least in theory. We've built space stations. We've sent probes across the solar system. So, why haven't we established a lunar colony? Is it politics? Funding? Or could it be that the challenges we've discussed are harder, more persistent, and more expensive than anyone anticipated? Every feasibility study, every mission plan, eventually runs into the same uncomfortable truths. The moon isn't just inconvenient. It is hostile, structurally, biologically, and physically. Why are most missions still conceptual? Even today, lunar missions are largely plans on paper. Concepts for bases, domes, and even cities dominate space expos and media coverage. But the gap between drawing a habitat in concept art and sustaining human life, their long term, is enormous. As we've seen, radiation, dust, thermal extremes, vacuum, and low gravity are not trivial problems. They multiply, interact, and sometimes defeat the best engineering solutions. So when agencies talk about returning to the moon, it's worth asking, are we talking about visits or habitation? Because the difference is enormous. Are Mars plans ignoring the moon's lessons? NASA, ESA, and private companies now turn their eyes to Mars. Yet Mars is even harsher than the moon in some ways. Thin carbon dioxide atmosphere, higher radiation exposure, months-long night cycles, extreme cold. If the moon, which is closer and theoretically easier, remains effectively uninhabitable, are we underestimating the biological and technical barriers on Mars? Perhaps our excitement blinds us to the lessons the moon is quietly teaching. Are humans biologically earthbound? This brings us to the most fundamental question. Are humans truly designed to live anywhere else? Every system in our body evolved under Earth's gravity, atmosphere, and magnetic field. Every cellular process assumes protection from radiation and environmental extremes. The moon doesn't just test our technology, it tests our biology. And so far, the evidence is stark. Biology doesn't bend easily to fantasy. Maybe we can visit. Maybe we can survive for short periods. But to call the moon home? That may be a question we still can't answer. What would living really mean? Finally, we must define what we mean by living on the moon. Does it mean breathing and surviving for a few days? Working in a pressurized suit with life support constantly at risk? Raising families safely? Sustaining health and cognition over years or decades? Survival and habitation are not the same. Many discussions confuse the two. True living requires stability, resilience, and autonomy, things the moon does not naturally provide. The unsettling gap between vision and reality. So here's the tension. Media portrayals, concept art, and optimistic mission plans suggest the moon is just waiting for us. Science, physics, and biology suggest otherwise. The moon remains both a symbol of human ambition and a mirror reflecting our limits as earthbound creatures. It asks questions we are not yet ready to answer about technology, biology, and the very nature of human survival in environments beyond our planet. And it leaves us with one lingering thought. Maybe the moon is not just a destination. Maybe it is a reminder that Earth is a home we were truly designed for. After exploring the moon's radiation, vacuum, temperature extremes, dust, and the limits of human biology, one thing becomes clear. The moon is not Earth, and that distinction matters more than we often admit. Perhaps the moon is best understood not as a future home for humanity, but as a laboratory, a proving ground, a place to test ideas and technology. It is a place to visit, to learn, and to challenge ourselves, but not necessarily a place where humans can thrive indefinitely. Even the most advanced systems have limits. Even the most sophisticated technology cannot completely counteract biology, physics, and environmental extremes. The moon exposes a tension between what humans can engineer and what humans can survive. There is a stark difference between visiting and living. One requires careful preparation for short-term survival. The other demands long-term adaptation to gravity, radiation, dust pressure, and thermal extremes. The latter remains a challenge we are nowhere near solving. This doesn't mean exploration is impossible. It doesn't mean humans will never set foot there again. But it does mean that the narratives of lunar colonization, those glossy illustrations of domes, cities, and thriving communities, may be more aspirational than realistic. So as you think about the moon, ask yourself, are we chasing dreams of habitation, or are we learning about the limits of our biology and technology? Are we imagining life there, or are we confronting what it truly would take to survive? The moon challenges us, humbles us, and reminds us that our home planet is not just convenient. It is uniquely suited to life as we know it. Perhaps the real lesson isn't about conquering the moon. Perhaps it's about understanding ourselves, respecting the laws of nature, and approaching space exploration with curiosity, caution, and critical thinking. In the end, the moon may remain a place we admire from afar, a place we visit briefly, and a place that teaches us the value of our fragile, earthbound existence. The question isn't whether we can go there. The question is, what does it really mean to live somewhere that was never meant for us? And maybe for now, that question is enough.